Hi, this is Dr. Habib Ahmed, and today I'm going to present the Silvaco TCAD simulation of various kinds of PIN photodetectors. So I'm going to give a short intro about photodetectors, and then later I'm going to talk about the Silvaco TCAD simulation of various kinds of PIN photodetectors. A photodetector is an optoelectronic device that converts light into electrical signals. Now it could be incident light or other electromagnetic radiations in the ultraviolet, visible and infrared spectral regions. So in case of photodetectors, the input is light and the output is electrical signal. Like for example, consider this PIN type of photodetector structure. Now generally a PIN photodetector is operated under reverse bias. So as you can see over here, the positive terminal is connected to the N-type layer and the negative terminal is connected to the P-type layer. When light is incident on this structure, and if the energy of the incoming light is greater than the band gap of the semiconductor, it's going to result in the generation of electron-hole pairs. Now the electrons would be attracted by the positive terminal and the holes would be attracted by the negative terminal, resulting in a current. Excuse me. This electrical signal is then sensed by the basic photoreceiver configuration. It is pre-amplified, amplified, and passed through a lot of other stages for various kind of applications. So in a photodetector, the input is electrical, the input is optical and the output is electrical. It's just like a solar cell. However, solar cells are large area devices, and the goal in a solar cell is to achieve maximum power. The goal in a solar cell is to achieve power generation. But a photodetector is a small area device. A photodetector is optimized for sensitivity and speed, and it has various applications in media or telecommunication, laser applications, medicine, biology, industry, defense, mining, and so many other applications related to physics as well. Now there are various figures of merit of photodetectors, for example, quantum efficiency, responsivity, spectral response range, response time, which also represents the response speed or the speed of photodetectors, and noise characteristics. Also, there are various types of photodetectors, which are photoconductor, PN photodetector, PIN photodetector, metal semiconductor metal photodetector, and avalanche photodiode. But our today's simulation is going to focus on various materials based PIN photodetectors. So I'm not going to go into a lot of the theoretical details of the photodetectors anymore. I have already posted videos on photodetectors. So if you go to my YouTube channel, and over there if you scroll down the videos, you will find a couple of videos about the theoretical part of the photodetectors. So there is photodetectors part 1 of 2 and photodetectors part 2 of 2. So now let us talk about the simulation part of the photodetectors. For that purpose, I'm going to run the deck build, which is the interface for running various kind of Silvaco TCAD programs. And here I have already made a code on silicon based PIN photodetector. So I'm going to open that first. It's saved at desktop. So here is my code, but generally like the font size of this text is really small in the DeckBuild environment, so I have copied the same code to a Microsoft Word document as well. So here you can see the code. We start with Go Atlas, and then we specify the meshing. In the meshing part, I am running a structure from 0 to 10 micrometers in the X direction. So here is the structure. As you can see, it's running from 0 to 10 micrometers along the X direction, and then from 0 to 1.7 micrometers along the Y direction. So as you can see, from 0 to 1.7 micrometers along the Y direction, where I have defined different regions along the Y direction. And also, this is a two-dimensional structure, but by default the third dimension or the Z dimension in Silvaco TCAD is 1 micrometer. Talking about the structure, I have defined 3 different regions. This is a P-type silicon region. This one is in intrinsic or lightly doped silicon region, and this is a heavily doped N-type region. Going back to the code, so my first region is running from 0 to 0.2 micrometers. As you can see over here, it's running from 0 to 0.2 micrometers. So I defined a sparser meshing at the origin point, and then a denser meshing at this interface at y is equal to 0.2 micrometers, because this is the interface of my P-type layer and a lightly doped, or you can also call it intrinsic type of layer. And then I have once again defined a denser meshing at 1.2 micrometers along the Y direction, because here I have another interface of the I layer and the N-type layer. And finally, I once again define a sparser meshing at y is equal to 1.7 micrometers. Here I am specifying my structure. So my region number 1 is silicon, running from 0 to 10 micrometers in the X direction, and from 0 to 0.2 micrometers in the Y direction, as you already saw in the structure. Then region number 2 once again is silicon, running from 0.2 to 1.2 micrometers in the Y direction. And region number 3 once again is silicon, it's running from 1.2 to 1.7 micrometers. I have assigned the top side as the anode and the bottom side of the structure as the cathode. Then I created the structure file with this name. Then I run the Go Atlas command once again, and I import this structure which I have already saved over here. Then I specify the dopings for different regions. For example, in region number 1, I have set the doping to P-type, and I have set the hole concentration to 1 into 10 to the power of 17 per centimeter cube. As you can see in the color chart, this region over here is P-type silicon with a hole concentration of 1 into 10 to the power of 17 per centimeter cube. For region number 2, I have lightly doped it with hole concentration of 1 into 10 to the power of 14 per centimeter cube. For region number 3, I have set the electron concentration to 1 into 10 to the power of 18 per centimeter cube. This is my region number 3. Then I specify some material properties. My material is silicon. I have set the hole recombination lifetime and the electron recombination lifetime to 2 microseconds. Excuse me. I live in Islamabad, and right now pollen allergy is really widespread over here, especially for outsiders, people who have come from outside and who live in Islamabad. It's a big problem around March, April. Anyhow, that was a sidetrack. So because of that, because of pollen allergy, I'm not feeling really well. Also, in case of photodetectors and also solar cells, we would like to define the refractive indices for excuse me, for the various materials that we are using in our structure. And if you open the Atlas user manual, here we have a database for we call it a SOPRA database. SOPRA files actually contain the refractive indices of various materials. So for example, my material is silicon. So if you scroll down to silicon, we see different options for silicon 100, silicon 110, and silicon 111 plane. I assume that my structure is based on silicon 111 planes. So, excuse me. So I picked silicon 111.nk and I've included that SOPRA file into my Silvaco TCAD code. Then I define models for running the simulation. I have included bipolar, band-to-band recombination, Fermi, Shockley-Red Hall, field mobility, concentration-dependent mobility, OJ recombination, optical. Print is used for looking at the runtime window outputs. And then also, we don't need to include this. We are dealing with a PIN structure under reverse bias. As already discussed that in case of PIN photodetector, we operated under reverse bias in order to achieve maximum depletion width. And this maximum depletion width results in lowering the capacitance, leading to high speed of the photodetectors. And then I have used the command of impact self. So since there is an I layer in my structure and I'm operating it under reverse bias, and if we are dealing with high reverse electric fields, then there could be excuse me, impact ionization as well. So I've included an impact model for impact ionization, which is Silberher model. Then I've included a method for the numerical simulation and also for convergence of my structure. Then I used output in order to see various output parameters. For example, the conduction and valence energy level, polarity charges, some band related parameters, the electron mobility, hole mobility, Shockley-Red Hall recombination, radiative recombination, OJ recombination, and permittivity, etc. I used this command for the initial guess of the simulation. Then I save the structure under thermal equilibrium and plot it under thermal equilibrium. After that, I want to look at the structure under light. So I have included beam number 1. Excuse me. I have defined the wavelength, and for this beam I have set the origin to 5 in the x direction and to -1 in the y direction. So if you look at the structure, our structure is running from 0 to 10 micrometers in the x direction and from 0 to 1.7 micrometers in the y direction, and the beam is around here at x is equal to 5 and y x is equal to 5 and y is equal to -1, so slightly above my structure. Then I'm using Newton method for numerical simulation and for convergence of my code. Then I want to bias the structure under reverse bias. So I'm running a cathode voltage from 0 to 1 volt with a step of 0.1 volts. Then I create a log file with this name, and I want to save the output file in the wavelength range of 0.1 to 1.5 micrometers. So for that purpose, I have used these commands. I want to look at the spectral response of my PIN photodetector from 0.1 to 1.5 micrometers. And then I plot this log file which I've created. I save the structure and I plot the structure as well. So here I save the structure once again because at this point I would also like to look at the photo generation rate inside my structure. Then I operate the structure under dark conditions initially, and for that purpose I create another log file with this name over here, and then I start running the anode voltage from 0 to approximately from 0 to minus 38 volts with an initial step of minus 0.01 volt and then minus 0.1 volt, and then I sweep it up to 35 volts with a step of minus 1 volt, and then from minus 35 to minus 38 volts I'm using a step of 0.1 volt. Then I want to look at the spectral response of my structure under light conditions as well. Basically I want to look at anode current versus I want to look at the current versus voltage response of my structure under light conditions now. Excuse me. So now I'm using another beam. I name it as beam number 2. Wavelength is also given at an angle of 270 degrees. X dot origin is equal to 5 and y dot origin is equal to 2. So in the structure from the bottom side over here, so the beam is around here. Then I initiate the beam initially at 0.001 watt per centimeter square, then I move it up to 0.01 watt per centimeter square, then 0.1 watt per centimeter square, and then to ramp it up to 1 watt per centimeter square. I create a log file. I sweep the anode voltage from 0 to initially to minus 37 volts and then to minus 37.5 using a step of minus 0.5 volts. Excuse me. And then from minus 37.5 to 38 volts using a step of 0.01 volts. Then I use the command of log off over here so that this log file does not continue to the next log file, which I've done it for under dark conditions. We logged off so that its values do not continue to the next log file, which is under light conditions. And then I use the command of overlay to overlay the log file under dark conditions and then under light conditions. And then I use the command of quit to finally quit running the program. So I have opened this program in my Silvaco TCAD environment as well. So let me run the simulation now. Here is my structure. We can right click on the structure, click on display, and click on this meshing icon, hit apply to see the meshing. So I have defined a slightly denser meshing at this interface and also at this interface. Right click on the structure, click on contours, go to define contours, and click on absolute net doping to see the dopings in the structure. So as you can see from this legend from the color chart, that this is my p-type layer, this is the intrinsic layer, and this is the or we can also call it the lightly doped layer, and this is the n-type layer. We have 10 to the power of 17 hole concentration for this layer, 10 to the power of 14 hole concentration for this layer, and 10 to the power of 18 electron concentration for this bottom layer. Furthermore, here is the same structure under light conditions. So if I right click on the structure and then I go to display, click contours, go to define, click contours once again, and here I want to look at the photo generation rate. So click on photo generation rate now, hit apply, and from the color chart you can see that the maximum photo generation is achieved inside the eye layer or close to the interface of the eye layer at this junction and also at this junction. Then I also want to look at the spectral response range. So I right click on this plot, go to display, and click on optical wavelength. So here I have plotted cathode current versus optical wavelength, and we can see that our spectral response range is approximately in the range of 0.2 micrometers to 0.8 micrometers, or we can say this photodetectors is responding to light in the range of 200 nanometers to 800 nanometers. I have also, now the simulation is ready for looking at the cathode current versus anode voltage under dark and light conditions. So we right click on this plot, click on display, and over here click on the anode voltage versus cathode current, hit apply, and click on log in order to see both curves. So then I hit apply and click OK. So here is the cathode current versus anode voltage plot in the range of 0 to minus 38 volts. This red curve represents the cathode current versus anode voltage under dark conditions, and the blue and the green curve represents the cathode current versus anode voltage under light conditions. And as you can see, there is, like, if I zoom in on these two curves, there is 8, 14, 6 orders of magnitude improvement in the current under light conditions as compared to the dark conditions. Or we can say the current on-off ratio is 6 orders of magnitude for light versus dark conditions. So here we see that under light conditions we get more current as compared to under dark condition. And this is critical. The more the on-off ratio, the better your photodetector device would be. Also, we see another effect over here at around, I would say, if I zoom in on this, around minus 37 volts. And this is because of the impact ionization effect. At this point, the field is now too high. So electrons inside the eye layer, they get enough kinetic energy to knock off secondary electrons from other atoms, and this process continues. resulting in drastic increase in current at this point over here. And this is because of the avalanche effect, and for that purpose I included the Silvaco impact ionization model into my Silvaco TCAD code. So I've compiled these results into the slides as well. Here is the structure, the photo generation rate, the cathode current versus anode voltage under dark conditions and also under light conditions. And then here is the spectral response of the photodetector. Now this is a silicon PIN photodetector. If you look into literature, you see that the spectral response of silicon-based photodetector looks kind of like this, where the spectral response range is in the range of approximately 400 to 1100 nanometers. Now the question is, why isn't my spectral response in this range? Excuse me. So to answer that, first we need to keep in mind that my eye layer thickness is 1 micrometer. And let's go back to the basics of photodetectors. So the spectral response range of silicon-based photodetectors is in this range, 400 to 1060 nanometers to be more exact, or we can say 400 to 1100 nanometers roughly. Now, for this spectral response range, we have a lower cutoff wavelength and an upper cutoff wavelength. The upper cutoff wavelength depends on the band gap of the semiconductor. It is dictated by the band gap of the semiconductor. For example, in case of silicon, the band gap is approximately 1.1 micrometers. So 1.24 divided by 1.1 approximately results in 1.060 micrometers, or you can say 1060 nanometers. Also, the lower cutoff wavelength of photodetectors is dictated by the absorption coefficient of semiconductors. For example, here is the absorption coefficient versus wavelength for silicon photodetectors. And without going too much into the theoretical details, here is a simple explanation. Light with longer wavelength travels deeper into the semiconductor. Light with medium wavelength travels up to medium distance inside the semiconductor. And light with shorter wavelength is going to travel shallower into the semiconductor. Now, in case of the Silvaco TCAD simulation for the PIN structure, over here, my eye layer thickness is 1 micrometer. So, this structure should be good enough to absorb lights with shorter and medium wavelengths, but the eye layer thickness in this structure is not enough to efficiently absorb longer wavelength light as well, because longer wavelength light has a tendency to travel deeper into the PIN photodetector structure. So what I did is I simulated another structure, and I'm not going to go into the simulation of it, but I'm going to show the results, where now my structure is running from 0 to 10 micrometers in the y direction, and here are the doping profiles. So I have the p-type layer approximately from 0 to 1 micrometer, and the n-type layer running approximately from 9 to 10 micrometers. So you can say that effectively my eye layer thickness for this structure is 8 micrometers. And then I performed the Silvaco TCAD simulation of this structure as well to look into the spectral response. And here you see that now my spectral response is running approximately from 400 to slightly above 1 micrometer. And now this is kind of replicating the theoretical spectral response of silicon-based photodetector. Also, I performed the Silvaco TCAD simulation of gallium arsenide on silicon-based PIN photodetector. So I'm going to open that code now. We go to File, Open. I've saved it over here in this folder. Open the code. And I'm going to open it. I'm going to open the code in Microsoft Word for better visibility for the video purpose. So here is the code. In this case, I will compile the results over here as well. I have not changed the structure dimensions. The structure dimensions are the same. Also, I have not changed the doping concentrations of these 3 PIN layers. However, I've set the top layer to P-type gallium arsenide, and this middle layer to I-type gallium arsenide, and this bottom layer to silicon. So, and then here is the code for the same structure. So basically the meshing is the same, the region dimensions are the same. However, as you can see that now region number 1 is set to gallium arsenide. Similarly, region number 2 is also set to gallium arsenide. Region number 3 is set to silicon. Similarly, the doping concentrations are the same as the previous structure for the 3 layers, the P-type layer, the I-type layer, and also the N-type layer. Since I'm using gallium arsenide in this structure now, so I'm calling the Sopra file for gallium arsenide as well. You can see that over here in the Atlas user manual. For gallium arsenide, we have these different options, and I'm using this one in order to include the refractive indices for gallium arsenide. And then the rest of the code is the same, but I just want to look at the spectral response range. So I'm quitting the code at this point, and here I'm not going to look at the current versus voltage under dark and light conditions. I'm just going to run it up to the spectral response point, and then I'm going to quit the program. So let us run the simulation. Here is my structure. If I right click on the structure, click on display contours, then go to define contours, absolute net, select absolute net doping from this scroll down menu, hit apply. Okay. Here are my doping concentration profiles. And here is but before that, I also want to look at the photo generation rate. So here is the structure under light conditions. I right click on the structure, click on display, then click on contours, go to define contours. Excuse me. And in the scroll down menu, now I select photo generation rate, hit apply. So based on the energy band gap engineering, we now observe that most of our photo generation occurs at this interface, at the I layer to N type layer interface. Also, I right click on this plot and then go to display and then click on optical wavelength as the independent variable and the cathode current as the dependent variable. Hit apply, and here is the spectral response for this structure. So effectively my spectral response range is in the range of 0.4 to approximately 1 micrometer. Now I'm going to close these. I'm going to close this one as well. I also performed the Silvaco TCAD simulation of this structure, which is gallium arsenide over indium gallium arsenide over silicon. So in this case, my p-type layer is gallium arsenide based. My I-type layer is based on indium gallium arsenide with a composition of 5%. As you can see, x.com is 0.05. So with a composition of 5%. And then my N-type layer is silicon once again. Similar to the previous codes, I have not changed the dimensions of the structure. It's running from 0 to 10 micrometers in the x direction and from 0 to 1.7 micrometers in the y direction. Also, the dopings are the same in the 3 layers, and I'm going to open the code for this structure. So I go to open. I go to this folder over here, and initially I want to run the 5% composition code. So I open this file. I have also saved the code in Microsoft Word document. So I'm going to open the code in there. So here the meshing is the same. The region dimensions are the same. Region number 1 is gallium arsenide based. Region number 2 is indium gallium arsenide based with a composition of 5% initially. And then region number 3 is silicon based. The doping concentrations in the 3 regions are the same as the previous codes. Now since I have 3 materials inside this structure, so I have included the SOPRA files for gallium arsenide, indium gallium arsenide, and also for silicon. And then the rest of the code is the same. So let me run the simulation now. Here is my structure under thermal equilibrium. And let us check the energy band diagram of the structure. So I'd go to tools, cut line. Then I draw a cut line across the entire structure. Left click on this plot over here. Then right click, go to display. I don't want to see absolute net doping, so I'm going to uncheck that. Want to look at the conduction energy level, at the valence energy level, electron quasi-Fermi level, hole quasi-Fermi level. Then hit apply. And I'm going to close this one since we already looked at that. So here is the energy band diagram of this structure. We have got gallium arsenide over here, which is a wide band gap material in the structure. Then we have silicon on the right side, which has a band gap of 1.1 electron volts. Its band gap is lower than gallium arsenide. And here we have the indium gallium arsenide, which is basically an alloy of indium arsenide and gallium arsenide. The band gap of indium arsenide, as far as I remember, is I think 0.35 volts. So the band gap of indium gallium arsenide is going to run from 0.35 electron volts to 1.4 electron volts approximately. So as this layer is indium gallium arsenide based, it has a narrower band gap as compared to the rest of the structure. I'm going to close this file now as well. Here is our structure under light conditions. So I right click on it to look at the photo generation rate. You go to controls. Then from here, from the drop down menu, I select photo generation rate, hit apply. And now we can see inside this structure that most of the photo generation occurs inside the I layer, which is based on indium gallium arsenide. And this is because indium gallium arsenide is a narrow band gap layer inside this structure. So most of the light is going to be absorbed inside this layer. So here I have used a composition of 5%, and then we can look at the spectral response of this structure as well. So from the drop down menu I used, I'm going to select optical wavelength, and here is the spectral response running from approximately 0.1 micrometer to 0.9 micrometer, or 100 nanometers to 900 nanometers. I've compiled the results over here in a PowerPoint document as well. You can see the energy band diagram, the photo generation rate, and the spectral response range. And in this structure, I've used a composition of 0.05 or 5% for the indium gallium arsenide layer. I performed other simulations as well. Like for example, I'm not going to show it here, but I saved the results. Excuse me. So in another structure, I used 10% composition in the indium gallium arsenide layer, and here is the spectral response range of that structure. And then I performed another simulation where I used 20% composition, and you can see the spectral response range of that as well. And then I performed another simulation where I used 30% composition in the indium gallium arsenide I layer in the PIN photodetector. You can see the spectral response range of this photodetector as well. In fact, we can look at this spectral response over a wider wavelength range as well. So we can include more optical wavelength range over here. We can increase the range of the optical wavelength. Then I also performed the Silvaco TCAD simulation of a gallium nitride over indium gallium nitride over gallium nitride structure. Once again, I've kept the dimensions of this structure the same, and also doping levels inside the 3 regions also the same. So I'm going to open that file into my Silvaco TCAD environment. And I've also saved it in a excuse me, Microsoft Word document. So here is the code. The meshing is the same as the previous structures. When the regions dimensions are the same. However, I've defined the top layer as gallium nitride, the middle layer as indium gallium nitride with a composition of 10% for indium in the indium gallium nitride alloy, and the bottom layer is gallium nitride. Similar to the previous structures, I've kept the carrier concentrations the same inside this structure, And now since I'm dealing with gallium nitride based structure, so I have included the corresponding SOPRA file for gallium nitride. And I did not find a SOPRA file for indium gallium nitride, so I used a SOPRA file of gallium nitride for that as well. The rest of the code is the same, so I'm just going to hit run in the Silvaco TCAD environment and let us see the results. So here is my structure. We can see the doping profiles excuse me, as well. And this is a p-type layer, I-type layer, and n-type layer. And I also want to see the energy band diagram of this structure as well. So I go to tools, cut lines excuse me, and I draw a cut line across the entire structure. Right click on this, go to display. Instead of absolute net doping, I want to look at the conduction energy level excuse me, valence energy level, electron quasi-Fermi level, and hole quasi-Fermi level. This is the excuse me, this pollen allergy has affected me badly today. Anyhow, so here is the energy band diagram of the structure. We have, as we can see from the energy band diagram as well, the Fermi energy level is closer to the valence energy level on this side. So we have p-type gallium nitride on the left side. The Fermi energy level under thermal equilibrium is closer to the conduction energy level on the right side. So we have n-type layer over here, and we have excuse me, I-type indium gallium nitride layer sandwiched in the center. The band gap of the indium gallium nitride layer is slightly lower as compared to the band gap of the gallium nitride, because here we have used a 10% composition. If we use 20% indium in the indium gallium nitride alloy, its band gap is going to be even lower as compared to the gallium nitride layer. Indium gallium nitride is an alloy of indium nitride and gallium nitride, and its band gap ranges from 0.67 for indium nitride to 3.4 electron volts for gallium nitride. Here is the structure under light conditions. So go to display, define contours. Excuse me. I want to look at photo generation rate. Anyhow, it's not really visible this way. The photo generation might be, so it has photo generation, but it's lower as compared to the previous structures. Then I want to look at the spectral response range, so I go to display and then optical wavelength, and here is the spectral response range for this structure, which runs from approximately 100 to 400 nanometers. Now, since gallium nitride is a wide band gap material, so it's going to pretty much absorb light in the ultraviolet range, but because its upper cutoff wavelength is going to be dictated by the band gap of the semiconductor. The band gap is 3.4. So 1200 divided by 3.4, I would say roughly you can say the upper cutoff wavelength is 400 nanometers, and it's not going to absorb light above 400 nanometers. These are the simulations of different PIN photodetectors. I hope this session was informative for you. Till next time, take care, and I will talk to you later. Bye.